Hi. One of the things we're going to be working on today is how to use this cool friction force equation that we've derived already. So, what we're going to do today, though, is we're going to start off with a quick question. When you look at a table, like the one you're sitting at right now, presumably, is it really flat? I mean, what makes something flat? Is it how it feels? Or how it looks? Or whether water rolls off one way or another? Well, to give you some idea, this is a zoomed in picture. Actually, it's an electron microscope picture of a similarly flat, quote unquote, surface. And as we look, we can see that there's little asperities. There's bumps. Even if the surface itself were perfectly atomically smooth, atoms themselves aren't smooth. And so you will always have some sort of friction as long as two surfaces touch each other. Where friction comes from is when those little bumps rub together between two solid surfaces. Now, you might be thinking to yourself, well, does it have to be a solid? Actually, yes, it does. Liquid frictions and air resistance are actually calculated similarly and do not obey this Newtonian relationship. So I really do want to focus on two solid surfaces. We can get into a discussion over what makes something a solid, but that's kind of getting beyond the scope of this class. So, things we know about friction. We know that friction and heat are somehow related to each other. If you come back and click this later, you should be able to go see how rubbing the yellow and green surfaces together actually changes the temperature. Now, why that would be is because these atoms and molecules vibrate together. And vibration of molecules is what we feel as heat. So, in terms of calculations, you saw our mathematical equation earlier, but you should also know that that equation gives you the magnitude of friction force. The direction of the friction force is different. The direction always works opposite the direction of motion. So, if you're going left, it goes right. If you're sliding downhill, it goes uphill. But it is a little bit more complicated than that. It works to oppose the motion between the two surfaces you're concerned with. If the surface is the box and the ground, and you're applying a force to the left, friction is trying to prevent this sliding of the box along the ground. In the case of the going downhill, the surface is the bottom of the ski and the top of the hill. This is important because sometimes people have the misconception that friction is always trying to slow the motion. That is not true. There are solid cases where friction causes acceleration of objects. For instance, if you ever left your phone on the dashboard and you accelerate your car, your phone goes with your car, and that's because it's accelerating as a result of friction. So, back to our Newtonian relationship that we got from our lab the other day. We found out that the force of friction depends on the surface materials that are interacting with each other and how closely they are pushed together. Notice that the two surface materials that are interacting with each other, well, that pair is symbolized by this symbol mu. A little bit grainy, my bad, but mu is the coefficient of friction. And how closely they are pushed together, I should probably work on the wording because it's not necessarily how close. Close is a distance. How hard are they pushed together? Hard is a force. So, how hard are they pushed together? That is your normal force. These two put together through simple multiplication gives us the magnitude of the friction force, and the direction, as we mentioned, is opposite the direction of motion. Okay, so tune in next time to go over some more details about the coefficient of friction and the other things that affect it. Thanks for watching.